Review. You can see that. What problems? Math is about problem solving. So what problems have we solved so far, or are in the process of solving, have we been working to solve? Okay, so, well, the first one is basic ignorance. Ignorance is a problem. We want to solve that with understanding, right? That's what mathematics is. We want to be less ignorant of the world. We want to understand things. And that's what mathematics is. Fine. Then we realized we could compute a whole lot of things. So computation is good, but bless you, we saw Thales's theorem that there's this computation you can do, and it's amazing, and the degree is always 90, and why, right? It's not satisfying, but not satisfying alone without knowing why. And so that means we need proof. Then we saw a proof of Thales's theorem, but the proof used at every stage other facts, right? Why is Thales's theorem true? Well, you need the sum of the angles in a triangle is 180 degrees, and you need that the base angles of an isosceles triangle are equal, yada, yada. So arguing in the middle of a proof, we need to use other facts that themselves need to be established. We get infinite recursion. This is true. It's not necessarily infinite. It could be circular also. Infinite, or I mean, it's still if it's circular or circular. You know what I mean by circular? Why is A true? I'll use B to prove A. And then why is B true? I'll use C to prove B. And why is C true? I'll use A to prove C. Circular recursion, i.e. A is true because of B, and B is true. Why is B true? It's because of C, and why is C true? C is true because of A. That's called begging the question. That's a logical fallacy where you're assuming the conclusion. Does that make sense? Why you don't want to have cycles like this? Yeah, I think it's clear. So what's the solution? Again, we're identifying problems and their solutions. Problem of ignorance, the solution is mathematics. The problem of computation, but not enough understanding, the solution is proof. We'll supply proof to any argument. Now we have a problem, infinite recursion of proofs. The solution is axioms, axiomatic method. We will declare, we will hold truths to be self-evident. Or the better way to say it is, we'll just declare certain things to be true. I declare that the sky is blue. I declare that whatever, the earth is round. I declare that between any 2 points there's a line. I'm setting I declare that a knight moves by moving 2 pieces up, 2 squares up and 1 square over. We're declaring the rules of the game. Better, we're declaring the rules of the game. Does that make sense? Okay, there was another problem when we talked about the basic, what are the objects? I told you what a knight is. Well, did I tell you what a knight is? A knight, I have to describe in terms of a pawn or a bishop or whatever. I have to describe, words are described in terms of other words. Since words are described in terms of other words, we will again have an infinite recursion. We will again face infinite or cyclic recursion if we try to give definitions to the most basic objects. Okay, that's the problem. Solution: undefined terms. I guess there are a couple more problems that we discussed. So in our theory, as we try to build up mathematics, we can have false positives as we try to build up mathematics, our mathematical theory, we may face false positives. What's a false positive? A positive is like when you prove something. So what's a false positive? You think you've proved something, but it's incomplete. Proofs that look okay, proofs that look, and I really mean look, with our eyeballs, that look okay, turn out not to be sufficiently justified. For example, what was the example that we saw? Yeah, proposition, the proof of the very first thing that Euclid tries to do is not justified. Proposition I.1, that circles intersect, was not justified. It was a glaring gap in our exposition of that proof, in our discussion of that proof. Right? Everybody remember that? We also, and we faced false positive. We also faced false negatives. What would be a false negative? Tell me again. Sayuri.
Using a theory, something that looks wrong.
Yes, proving something, exactly right. Sayuri says proving something that looks wrong, but actually isn't. There's no contradiction. What's an example of that? That we saw, other than Vaibhav. Actually, did you say anything yet today? Vaibhav.
Like, assuming the sum of all angles and triangles, does that mean then proving that two angles with equal angles are congruent?
Exactly right. That in hyperbolic geometry, angle implies not just similarity, but congruence, right? That's a false negative. Sim? Yeah, well, there was a debate about the fifth postulate, whether it was right or wrong, but there was no sort of definitive, I mean, in a sense, there was a definitive claim since Euclid claimed he needed it. He used it. He stated it as a postulate. So obviously he's stating it because he wants to use it and he thinks it's necessary for him to use. And moreover, debate about which postulates, which statements should be postulates versus postulates and axioms versus theorems versus consequences of more basic facts. The example being the parallel or the fifth postulate. Great. Okay, and so that's the problem. What was the solution? The solution to the fact that with our eyes we might get in trouble and prove false positives, prove things that we haven't actually fully justified, or we might prove things begrudgingly, thinking that there's something wrong with it, but actually there's nothing wrong with it. So that would be a false negative. We're trying to find a contradiction that doesn't exist. So the solution is we're going to work purely formally. Yeah, the solution is work completely formally. Every single step is going to be justified down to the point where a machine, at the time this was that Hilbert was thinking about this, he was thinking of a machine that cranks. This was the Industrial Revolution. So he's thinking about like just a big crank that spits out mathematical theorems. Of course, now we're going to do it digitally. Okay. So does this make sense? This is what we covered last week. We want to understand things. We want to solve ignorance. In order to do that, well, finding facts isn't good enough. We want to have reasons. We need proofs to go along with that. Proofs generate infinite recursion, so we need to have the axiomatic method. In the same way, definitions get an infinite recursion, so we're going to start with undefined terms. We don't want false positives. We don't want false negatives. We're going to work purely formally. What happened? Okay. That page is done. We're next page. Okay. So far, so good. Where did we end up? Where did we end up last time? We got a whole bunch of stuff. We opened up the library. We got undefined terms. Opened the library and got undefined terms. These are things called types. Does this work? Nice. And if I scroll up, you guys can see. So this is what we started with. We stated, I think I can just click that. And so we stated a definition of equilateral triangle. Equilateral triangle. That was this. We filled in some more axioms. Which axioms did we fill in? Yeah. Oh, come on. Which axioms did we fill in? We said you need to know how to specify whether a point is on a line or not. We said there's a postulate that given 2 points, there is a line, so that both points are on that line. We know when a point is on a circle. We know when a point is the center of a circle. Given a point that's meant to be the center and a point that's meant to be on the circle, we can create a circle with those properties. There's a distance function. There's a predicate for when circles intersect. That's just a true false. Doesn't mean we know when circles intersect. That's what you're about to tell me. And then if circles do intersect, then there are 2 distinct points at which they intersect. So those are the axioms that we've added so far. We filled in some more axioms. Let me come back to the homework in just a second. Then we started the proof of proposition. Then that's too low for you in the back, right? Rodrigo, you can see that? Then we started the proof of proposition I.1. And this is how far we got. So I'm just going to copy everything. Okay. We started the proof of proposition I.1. We were given 2 points. We want to know that there exists a point C so that ABC is equilateral. We started the proof. And step 1 was to construct this circle alpha. Step 2 was to construct this other circle. And that's as far as we got. Okay. So hopefully I now have it running here. And it looks like I do. Okay. Did anybody actually try this over the weekend? Did anybody open up code spaces and try to play with it? It's okay if you did or didn't. Is Jiven the sole code spacer? Will you teach the rest of us how to do this properly?
I wasn't sure. I mean, I know there's one assumption to make. I wasn't sure what you have to do. Is it the first assumption I thought you could make is that if you have a line, you can find the points of intersection on a segment of that line?
Wait, sorry. You're telling me something technical about the actual axioms. I'm asking a much dumber question, which is before we can get into the axioms, how does everyone get to run this thing on their own computer at home? You click the link that I gave was good, right? That's my question, is if you click this link, you actually get to it and you can click the button. Did anyone other than Jiven try that? Alex, you tried it?
I opened it.
You opened it and it worked?
Yeah.
And you were able to copy this stuff and paste it in and
That's all.
that's all. Great. That's all I asked you to do. I didn't ask you to do anything beyond that. Tonight, try clicking the link because pretty soon you're going to want to be able to do this at home. Okay, so let me add this little bit of homework. It wasn't homework yet. A little bit of homework. Click the link from lecture 4 and just see if you can get this software running in your browser. Okay, does that make sense? Now, what's that? Whoop, whoop.
Can you do that?
Well,
Or you mean a link that like create your own?
well, I gave the link here and I did it on my computer, but I didn't ask you yet to, at home, also click the link, log into GitHub and make sure you can do what I'm doing here.
Oh.
So now I'm asking you, try and just report on your homework. Yes, I succeeded, or no, I did not. Okay, something about it didn't work. I want to make sure that we troubleshoot anything about the technology we need. This course is not about technology, right? We're doing everything on paper. We want to think. But the technology is A, fun to play with once you get it going, and B, can help you with your homework if you want to use it that way. It's like I'm trying to get you set up with a calculator. And we're going to have a bunch of times tables. You can do them by hand, but if you want to check them with a calculator, it's good to have that tool. Does that make sense? Okay, so homework 5 is click the link from lecture 4. And in fact, I'll make your lives easier. I can copy and paste. There's the link again. So I don't even have to say from lecture 5. Click this link. There we go. Click this link and just see if you can get the software running in your browser. Okay, now let me recurse back to Jivan. You were saying something about you were changing the definitions. You're adding some more
Yeah.
basic axioms.
I wasn't sure one. The first one I found for that is that if you have a line, you can find how many intersection points there are on a segment of that line. Is that
Interesting.
far?
That's a little farther than what I was going to do first is let's go over your homework.
Yeah.
Because the homework was we want to now have some mechanism by which we can say, yes, two circles do indeed intersect.
You just do what's the radius of a circle? Is that
No, that's okay. So let's talk about, okay, so now let's talk about your previous homework. When do two, we're going to make an axiom, but that axiom should reflect reality. So what is the reality? How do we engineer the axiom so that it's useful and represents what we think is going on? When do two circles in the Euclidean plane actually intersect? What is a good characterization of that occurrence, phenomenon, whatever occurrence? That's not right. Is that better? How do you spell occurrence? Was I right the first time? I guess so. No, that's not right either. You're not going to tell me? Phenomenon. What is good characterization of that phenomenon? Okay. Did I see a hand over here? Sanvi?
So I did absolute value R1 minus R2, which is like the radius of circle 1 and radius of circle 2.
Okay, let R1 be the radius of one circle, be the radius of one circle, and go on. R2 is the radius of the other one.
R1 minus R2 is less than distance, which is less than R1 plus R2.
Is less than the distance between what?
Radius of circle.
You mean the center?
Yeah.
Between centers, distance between the centers. Okay, and that's less than
R1.
R1 plus R2. And I guess now you don't need absolute values. Okay, that is what do you guys think of that? I like that. Is that what, Jivan, you were going to say? Is that what everybody did? Okay, why does this condition work? Sure. No, make it up again. You found it once. Yeah.
It's like a bunch of
It's a bunch of formulas.
Yeah.
So let's think about it. You have 5 different formulas. So there are 2 basic things going on. One is that the distance between the centers might be so far that the radii are just not big enough to get there. Right? Another one is that maybe the centers are close together. Here's 2 centers that are close together, but 2 circles that still don't intersect. So this.
Not conditions, but like things that don't really work. Like one of them was that the circle inside would be tangential to the circle on the outside, and then it would be vice versa, and then it would be no solution, meaning that it would be completely like different. And then there would be the same circle.
Uh-huh.
It was, like all solutions, and there was one more. I think it was another no solution.
Okay.
And it was like It was one circle's like entirely beside the other. without-
Okay, okay, I like it. You guys got another one? What's happening? Soham, what did you say? You're confused. Sorry. Let's take it back. The confusion is about what?
Well, I'm just like, what were we looking at? Like the
Bef-
circle.
Different scenarios.
Different scenarios. What we're looking at is scenario. We're trying to understand when do circles actually intersect. So let's look at examples where pairs of circles don't intersect. So this circle, I guess it's calling it E, and this circle is calling it F. So circles E and F don't intersect. Why not?
Oh, I get it.
Their centers are too far apart.
Yeah.
Circles H and K also don't intersect, but it's not because their centers are too far apart. They're too close relative to the radii. So where's the sweet spot? And Sanvi is saying that it's the distance to the centers has to be much less than the sum of the two radii. So it's not too far apart. Also, it can't be closer than the difference of the two radii, because then one circle will be inside the other. Does that make sense? I like that. I like that as a mathematical definition. It's a little tricky to deal with formally because then we need a notion of radius. And in order to say what a radius is, in fact, we haven't even specified what a circle is. What to say what a radius of a circle is, we need another map from a circle to a real number to speak of its radius. We can add that, actually. Let me propose, did anyone do it a different way? There's a variety of ways that you could have thought of engineering this predicate. Jevin came up with something else. Did anyone else come up with anything else? Ion, what did you come up with? Same thing as this, or?
Yeah, yeah.
Okay. Who else did the same thing as Sanvi? Everybody did the same thing as Sanvi. Pretty sure, did you do something different? What did you come up with? Same thing, okay. Ashley, did you do anything different? No one did anything different other than Jivin. All right, Jivin, what did you do?
I was second earlier. I created a new chart for a line segment.
Okay,
And I used that to find intersection points between the circles. And if the centers of the circle are far apart, where the line segment has two intersection points, and they're close enough so the radius are the radius. Okay, yeah. And then, yeah.
okay. Let me propose, I like that idea. Let's go with that idea. Let me propose, it'll be useful to have, I agree, it'll be useful to have another notion. If two circles intersect, let me slide this over a little bit. If two circles intersect, then check this out. There's a point on one circle, there's a point on P that's inside the circle Q. And similarly here, this point N is on the circle Q and inside the circle P. Wouldn't that be a sufficient condition so that we don't have to check, like absolute values and distance of the radii, and these are two inequalities, they have to check two different things. So we could say, let me proposed predicate, proposed way to tell if two circles, or at least give a condition that says when two circles intersect. If there is a, let's say we're given two circles. If we're given circles, what are we calling circles? Alpha and beta or something? Alpha and beta. If there exists a point A, which is on alpha and inside beta, we don't have a predicate yet for inside, and there exists a point B, which is on beta and inside alpha, then the circles do intersect. Does that make sense? Yeah.
But wouldn't this not work if circles are inside each other again? Then
If the circles are inside each other, let's think about that. If the circles are inside each other, then the point J, which is on the circle K, is indeed inside circle H. But I don't have another point, which is which is inside this circle and on that circle. You see, it knocks out both conditions at once. Does that make sense? You guys like this option? So so let's add a few things. So following this idea, let's add a few axioms. So one axiom, let's add the following. So first of all, we have something called point on circle. Yeah, Baba?
Wait, for your intersection, like, we're just looking at the overlap of the area, or just like intersection have to be that arc intersection?
I want to know when there will be these points. When will I have two distinct points where the circles intersect? And I claim that a necessary and sufficient condition in Euclidean geometry is if there's a point on one circle that's inside the other, and there's a point on this circle that's inside that circle. And that is exactly the condition that captures whether two circles intersect. Does that make sense? Let's try to write it formally. So we have, as I was just saying here, we have something called point on a circle, which is meant to represent a point being on a circle. Should we have something called point in a circle? Point in circ. And what kind of thing is that? Point to prop. I'm sorry, point to circ to prop, exactly as Jivan said, right? Give me a point, give me a circle, I'll give you a yes or no. Are you on the circle or not? So point to circ to prop. And now we can state what it should mean for circles intersect. Circles inter if what do we want to call this thing? Give me a name. Sarah, give me a name.
Sarah.
Okay, let's call it Sarah, and we'll figure out another name for it in a minute. Sarah is the fact that for all points A and B are points, and alpha is a circle. Alpha and beta are circles. Then, if A is on alpha and B is on beta, and A is inside beta and B is inside alpha, then alpha and beta do intersect. Jeremiah.
But yeah, but does the program know what classifies inside?
No, we have to specify that, and we're going to in just a second. Okay, yeah, this is just, these are very you're learning something very, very abstract. So if this is hurting your brain, like, that's the point. We're stretching your brains into this abstract way of thinking. Yeah. Okay, so do you want to take a minute and write that on your page, write what you think Sarah should represent? And then let's see if what we write here is equivalent to that. Navia, I lost you. What are we trying to do? What are we trying to come up with here? Okay, we're trying to come up with a way of saying that we're given circles A and B and points, we're given circles alpha and beta and points A and B. And the condition is if A is on alpha and A is inside beta and B is on beta and B is inside alpha, then the circles alpha and beta intersect. And the picture that we have in mind for that is exactly this. So this is, can I rename this A? Rename. I'll call that little a. Okay. And then this one I'll rename. And this is little b. And this circle I'll rename to alpha. Which one should it be? I think it's alpha. Nope, beta. Beta. Okay, yes. Hello. Please? Have I broken GeoGebra? Okay, no, no, okay, that's gonna be P. Okay, so Oh, I had this backwards. Oh, it can't be. I don't know what's going on. This is supposed to be alpha. Do I have to start over? Navi, are you with me? This is A, and this circle is alpha. And this is B, and this circle, despite being labeled alpha, is called beta. And A is on alpha, and B is on beta. And A is inside beta, and B is inside alpha. And that's the condition under which they intersect. So how would we start writing that? How would we say that A is on alpha? Yep. Exactly right. Point on circ. And then I have to give it a point A, and I have to give it a circle alpha. Beautiful. So if we're given that A is on alpha, and we're given that A is inside alpha, A is inside beta, how would I say that? Point in circle. That's this new thing that we just came up with. Point in circle. Point in circ. If A is inside beta, beautiful. And, okay, still going. A is on alpha, A is inside beta. What else do we want to say?
Point on circle.
Uh-huh.
B.
B is on beta. And B is inside alpha. Then how do I say two circles intersect? Circles inter with what circle? They have to give it two circles.
Oh,
Alpha and beta. Circs inter alpha beta. Navia, great job. That was tough. Navi. Well, we're gonna give Sarah another name.
Oh.
Sarah proposed the name Sarah. It's representing when two circles actually do intersect. So this is just the predicate saying they do, but it doesn't say under what conditions they intersect. So what are the conditions under which they actually intersect?
It's a name.
What's that?
It is like representing.
This is representing that, yeah.
Shouldn't it be a definition? Why is it not Axiom?
So this is capturing, just like point is also a definition. It's capturing the structure of everything that we're going to use. So we want to put, well, as few things as we need to into this. But this is setting up, think of this as like anything that would be in the rule book for chess needs to go here. So there are things called pawns, and there are things called knights, and there are things called whatever, and then this is the rule for en passant. And it's not a rule outside of the rule board, it's inside the rule board.
Wait, so why was equilateral triangle outside as a definition?
Because equilateral triangle is outside because it is something that's not part of the rules. It's like saying, you know, here's a situation where you have a pawn chain. A pawn chain is not part of the definition. It is something that's useful when you're thinking about, you know, structures. So we want to be able to say what we mean by an equilateral triangle, but that's not something that needs to be in the rule book. Does that make sense?
Yeah.
Okay.
Isn't the and symbol that little like caret?
Yes.
So shouldn't it be the and symbol and not those arrows here?
So that's a great question. And the reason that it's not and symbols but arrows is that this is a logical, this is a good thing. We added a few new axioms. Let me just record what the axioms are. Let me Khalil's question. Why arrows and not and symbols? Let me come back to that in just a second. I want to record what the axioms were. And in order to record it, I want to give a better name for. We could keep it Sarah, but then, now that we've written it out, it's good to have a temporary name. We've written it out. What should we really call this? Yeah, in fact, circles intersection. In fact, we should make this an if and only if, and not just a condition. Circles intersect if and only if there exists a circle, there exists a point on one that's inside the other, and conversely. Okay, so we could, maybe that's a good name for it. Circs inter if and only if, and if and only if what? So let's make it like this. Instead of being given the 2 points A and B, we're just given the 2 circles alpha, beta, and we'll say circles inter if and only if the following holds. So for any pair of circles alpha and beta, they intersect if and only if there exist points A and B, so that, and now it's going to be ands, so that this and this and this and this and that. Okay. Okay. Jake. So now let me explain why it was an arrow. I guess I'm going to have to explain it in some other context. When your conclusion, okay, so let's talk about arrows versus symbols. Let me grab an arrow so I can put it here. Why arrow and not the and symbol? Why arrow and not and symbols? Okay, great question. Let's talk about this. If you're trying to prove, if you're trying to prove P and Q imply R. So P is if it's raining, and Q is it's slippery, and R is you trip. If it's raining and it's slippery, then you trip. This is logically equivalent to P implies Q implies R. This is slightly subtle. So if you don't get what I'm saying, just think about this. Let me make this optional. This is a star problem. Why? Why are those two things logically equivalent? Okay, and you can think about, well, if P is true and Q is false, or if P is false and Q is true, or both P and Q are false, then what are we trying to prove? And compare that to the truth table of P and Q. You know what I mean by that? This is a kind of coding rule. Modus ponens, you're thinking of?
Maybe. I saw a video about this.
Modus ponens, let's record this rule because it's a useful one. Modus ponens is the rule that if you know that P implies Q, and you know P, those two things together imply. If you know that P implies Q and you know that P is true, then you know that Q is true. Okay, so that's often called modus ponens. Okay, so if you're trying to prove, if you have lots of assumptions and you want one conclusion, it's actually better to write it as the first assumption maps to the second assumption maps to the conclusion. That's technically better when you're formalizing just because it uses fewer parentheses. Like the first one, I have to give you P and Q at the same time, whereas this one is a little bit lazier. I can give you P, and then later I can give you Q, and then I can give you R. There's a technical reason for this. Let me not go into it now. Yeah, sure. But if you're trying to prove that P implies Q and R, then you can't turn the and into an arrow. Those are not logically equivalent. Okay, Khalil, does that answer your question? So the conclusion wound up on the other side. We said circles intersect. This if and only if is actually two things. There's a forward direction and a backwards direction. So the forward direction is if two circles intersect, then there exist points A and B. So that point A is on alpha, point B is on beta, and point A is inside beta, and point A is inside, point B is inside alpha. Conversely, if such a thing exists, then the circles intersect. Okay, so circles inter is a good name for it. But at some point, you guys were starting to say, we don't actually have a definition yet of what it means for things to be a circle. We've never said what it means to be a circle. Right? So let's give that definition. Let's call it point on circ if and only if. Okay, so we're given for all points A, B, and C. You'll see in a second why we need a third point of type point. And for all alpha of type circle. So let's say A is the center. How do we say that? Center of circ. A alpha. And B is on the circle, point on circ B alpha. Then I want an if and only if statement. I want to know C is also point on circ C alpha, if and only if what? So again, let's read this. We have 3 points, A, B, C, and we have a circle alpha. A is the center of the circle. B is a point on alpha. What's the condition under which C is also on alpha, other than J? Allison, can I pick on you? This is the literal definition of a circle. So let's go back to our picture here. No, that's not what I meant. What happened? I clicked stop share because Zoom got in the way. Go away. Here we are. Here's a circle. Okay, so we have points. We have points A is the center of the circle, B is on the circle, and I have a point C somewhere. How do I tell if C is on the circle or not? This point is C. When is it on the circle? Other than Khalil, other than Vaibhav, other than Sanvi, other than tell me again. Sayuri. Other than Sayuri, other than Ayan. Abi, was your hand about to be up? No, that's just a pencil in the air. How can we tell if this point is also on the circle? Yeah. How do we say that? We have a notion of distance. Yes.
The distance from like point L to O is the same as the radius.
Exactly right. And why did I need another point? We don't have a notion of radius.
Oh, so from point L to point N, you found the radius. And point L to point O, the radius is the same.
Beautiful. Beautiful. Exactly right. Does everybody see that? So the condition is the distance from A to B, which is the radius, is equal to the distance from A to C. That's the condition. Now we've actually defined a circle. This is the first time that we have a clear definition of what a circle is. So this is, now we define a circle. Okay, so that's what it means for a point to be on a circle. In order to be able to access this circles intersect, we also need a point to be inside a circle. So here's your challenge. In the next 2 minutes, what would point in circ if and only if look like? Write it down on your page. And give me a thumbs up when you got it. Ayan. Sure.
Can we use like any variables or should we use the same one?
If you want to use different variable names, you can. I think it's useful to just keep similar variable names floating around.
Wait, what is last line.
The last line? So we have points A, B, and C, and a circle alpha.
With the center.
We're assuming that A is the center of alpha. We're assuming that B is on alpha. Then, C is also on alpha, if and only if the distance from A to B is equal to the distance from A to C. So that's saying that C is at the radius distance over.
Okay. So it's like, so.
Okay, Jeremiah's got it for us. Oh, you don't, you have a question? You have it. Yeah.
So it's like the radius would be the point or the center alpha to A, right?
Distance A to B is the radius.
A to B. So then it would be if the distance from the center A to the new point C is less than that radius.
Beautiful. I can just copy exactly this whole thing. And say A is on the center. I'm assuming that A is the center. I'm assuming B is on the point, which means we have a way of saying what the radius is. Then the point C is inside the circle, if and only if the distance from A to C is less than the distance from A to B. In fact, maybe this one looks nicer just to make them similar. This new distance that I want to think about, the distance from A to C, is equal to the distance from A to B. Okay, so now we've defined the interior of a circle. We've defined what it means to be a point on the circle. We might be able to make some progress. Does that make sense? Now, how about the center of a circle? How about the center of a circle? We need a little theorem. What we would like to do, okay, so look at let's just remember what we've done. Here's the prop 1.1. And we have 2 points A and B. We want to show there's a point C so that we get an equilateral triangle. Step 1 was that there does exist a circle, alpha, with A on alpha and B, A being the center and B being on it. And then we obtained that circle. So now we have the circle alpha with A at the center and B on alpha. Then we did the same thing with step 2, was we got a circle beta with B as its center and A on it. We want to be able to, next step is to claim that the circles do intersect. Circles do intersect. Okay, so let's call that step 3. Step 3 is the fact, what do we call that? Circles inter? Circles inter alpha and beta. Okay, and we have to give a proof of that. Is it circle inter or circs inter? Circs inter alpha beta. Let me postpone the proof. I don't want to prove this right now. I don't want to prove this right now. Let's see if we can complete the argument, if we can complete the proof, postponing this part. That's called sorry. Sorry means I'm not going to give you the proof right now. Don't give me an error message. Okay, sorry is our way of apologizing to the computer that I don't know, I'm not going to give you the proof yet, but I claim that circles alpha and beta do indeed intersect. And look at what it's given us. It says, okay, you know, you don't have a complete proof, but let's just assume you can prove that they intersect. How would we finish it? Jeremiah, I lost you? Not really. Assuming they intersect, then what, Javen? Yeah, if they intersect, then that's called points of circs inter. If they intersect, then there exist 2 points. Okay, so let's give that a name. This is going to be step 4. Step 4 is the claim that there exist points. Now I'm going to call them C and D since we already have A and B. C and D of type points such that C is on alpha and C is on beta, and D is on alpha and D is on beta. Point on circ C is on alpha, and point on circ C is on beta, and point on circ D is on alpha, and point on circ D is on beta. And why is that true? Because they intersect. So this was called circs inter points of. The if and only if is how you prove that circles intersect. But if they do intersect, it's called points of circs inter, and I feed it step 3. I guess I have to give it alpha and beta and step 3. So let's see, there's an error. Alpha and I see. I set it up the other way around. So like this. I think that'll work. So C is on alpha and D is on alpha, and C is on beta and D is on beta. Now, C is on alpha, A is on alpha. B is on alpha, D is on alpha. A is, oh, and they're not equal. And they're not equal. That's what I was missing, that C is not equal to D. There we go. Okay, so this points of circles inter AB says exactly that. There exist points. So this step 4 tells us that there exists points C and D, where C is on alpha and D is on alpha and C is on beta and D is on beta and C and D are not equal. That's what the whole condition is, Jim.
I didn't know that was like why was an error in there?
The error, so let me show you what the error was. So I'm going to comment out this part. If I didn't have the C and D, then it's complaining that it says right here, type mismatch. It says type mismatch. What you said was points of circles inter, the type is for whatever the conditions are, there exists, and we were calling them C and D, there exists A and B, so that all of these things are true. But what you told me, what I'm trying to construct, is the fact that C is on alpha and D is on alpha and C is on beta and D is on beta, which is not the same thing because this has one more step in it, which is that A is not equal to B. So until I added this and C is not equal to D, couldn't prove it because they weren't literally the same thing. This is what I mean by we're no longer using our eyeballs. Okay? So let me give you homework. Homework. Given that we've proved this step 4, we don't yet have the points C and D. What is the next line of the proof? What is the next formal line in the proof? How do we get the points C and D out of step 4? And the hint is just look at what we did for steps 1 and 2. Look above. What's the syntax for getting out those points C and D?
Can you define somewhere what some of these symbols, like the comma and the colon equals? It's like I look at it and I'm just like,
Yeah.
I understand what everything between them means.
Yep.
But then I just get confused as to like
Recall the syntax. Have then the name, whatever you want to call it, name, then the colon, then the fact that you want to prove, fact to prove, and then colon equals, and then the proof. Okay, so have step 4, the fact that we want to prove is there exists a thing, and colon equals, why is it true? All right, guys.